Okay, class, this video is on Hess's Law, so this is section 5.4 Nelson. Hess's Law is pretty much just adding different reaction enthalpies to get to the final one. So let's get on with it. So here we have a diagram representation of Hess's Law. You start off with your reactants, so in this case it's nitrogen and oxygen, and then you have your products at the very end, which we're looking at is NO2. But what happens in between is there's an intermediate product formed, and that's nitrogen monoxide. You have to take this into consideration because there are different enthalpies that take place along the way. So we have to take this part of the equation into consideration, and that's where Hess's Law comes in. So let's take an example with this one right here. Hess's Law states that the heat of a whole reaction is equivalent to the sum of its steps. Okay, so let's take the example of carbon plus oxygen to give you CO2. This doesn't actually have it in nature. It's not a one-step reaction. There's actually two different steps to it. So you have carbon plus half O2 to give you carbon monoxide, so that's an intermediate. And then this carbon monoxide goes on to form or react with another half O2 to give you CO2. Now again, this reaction occurs very quickly, and it occurs with billions or even billions of different particles. So this is, we're just singling it down to one specific reaction. And now you have your delta H values that are associated with each step. So let's try to figure it out. What we do is we can break this down into two parts. We have the reactant side and we have the product side. So you can only add reactants with reactants, and you can only add products with products. So if you were to add these two together, you would have carbon plus carbon monoxide, and then half oxygen plus half oxygen. That gives you 1 full mole of O2. On the product side, you have only carbon monoxide and carbon dioxide. There's nothing else to add. So let's see how this works out. So first you have carbon, carbon monoxide, and 1 mole of oxygen because you add a half and a half. And then on the product side you have carbon monoxide and carbon dioxide, which is what we had thought would be. Now you do the same thing with the molar enthalpies. You just add them together. So negative 110 plus negative 283, that just gives you a bigger negative number. You come up to negative 393.5 kilojoules. Now over here we have two things that are the same. So you have carbon monoxide on the reactant side and carbon monoxide on the product side. What you can do is just cross them out, so they won't be in your final equation. So when you cross them out, you get what we were looking at, carbon plus oxygen to give you CO2. And this is what our initial target reaction was. So Hess's Law allows us to add equations. We add all the reactants, all the products, and all the delta H values that are given. Okay. We can also show how these steps add together, and this is in an enthalpy diagram. So if I go back, right here, we start off with N2 and O2 at a very low enthalpy or low potential energy. We go up to NO, which is an intermediate, and this required a lot of energy input. But then as that breaks down into NO2, you have energy that's being given off. So your final reaction, the overall step, is 90 plus negative 56. So I'll just put that down. So the first step plus the second step, and that gives you a final molar enthalpy of 34 kilojoules. Okay. Okay, so there's some rules for applying Hess's Law. The very first one, if you're going to reverse an equation, the delta H sign has to change too. So if you had a delta H that was a value of, let's say, positive 100 kilojoules, if you use a reverse reaction, then you have to change the sign as well. So then the delta H value becomes negative 100 kilojoules. And second rule, if you alter the coefficients of a reaction, you must do the same to the delta H. What that means is, let's say I have carbon plus half O2 to give me CO. If I wanted two of those reactions, I would double it. So I would say 2 times carbon, 2 times half O2, 2 times CO. Then I would have to double the delta H value as well. Okay. So here's a reaction that we can try. Enthalpy change for the formation of 2 moles of NOs. Now it's specifically stated that you want 2 moles of the product. Okay, so you can see where this is going. And we don't know what the delta H value is, but we are given 2 steps that occur for this reaction. First one is half a mole of nitrogen gas plus O2. It gives us NO2, right? And this is not the product that we want, so we know this has to be cancelled out some way. And then we have NO plus half a mole of O2 and NO2. Now this is the product that we want, nitrogen monoxide. and we want 2 of those. So we know that we're going to have to flip the reaction, so reverse it, and we're going to have to multiply by 2. Now these are the values of delta H that are given for these specific reactions. So let's take what we know and let's apply it. So set up the known equations to get what you want. So we want our reactants on the left side and we want our products on the right side. So for the very first reaction that was given to us, we can keep it as it is. We don't have to reverse it. But we're going to multiply by 2 because we don't want half a mole of N2. We wanted 1 mole of N2. That was in the reaction. That was in the target equation. We wanted 1 mole of nitrogen gas. And then we have NO2. This is an intermediate product. We don't want this. So now here we have delta H, which was 34 kilojoules, positive 34 kilojoules. Because we're multiplying this whole equation by 2, we have to multiply the delta H value by 2 also. And our second reaction, we had NO plus half a mole of O2 to give us NO2. Now we wanted NO on the product side, so we want it on the right side. So what we're going to do is reverse it. To reverse it, we put a negative sign. And also we wanted 2 moles of NO for our final product, so we're going to multiply by 2. The same thing we do to our delta H value. And it's important to note here, because it is a negative, we're going to have to put a negative sign as well. So it's going to be negative 2 times. So when we do all this math, this is what our equation looks like. N2, because here we started with 2 times a half, so that gives us 1 mole of nitrogen gas. 2 times 1 mole of oxygen gas, so that's 2O2. 2 times 1 mole of NO2, that gives us 2 NO2. This is our product right here. Or sorry, this is an intermediate right here. We want to get rid of this. How does that happen? Let's go on to the second equation. Here we have negative 2 times NO. So here, there's our product. There we go. And because it is a negative, it reverses this, so it goes on the right side, just like we wanted. Negative 2 times half a mole of O2. So what the negative does, it puts it on the product side. And 2 times a half, you get 1 mole of O2. And then we have negative 2 times NO2. And what that do is, actually, this is the one that belongs here. This one is from the previous equation. Now you'll notice there's 2 things that we can cancel out right here, because they're on opposite sides of the reaction. And then we can cancel out 1 mole of O2. So this will become 1 mole, and this 1 mole right here will cancel it out. So essentially what we're left with is 1 mole of nitrogen, like we wanted, 1 mole of oxygen like we needed, and 2 moles of nitrogen monoxide, which is a product that we wanted. Now there's only one thing that's left, which is our delta H values. So for the very first reaction, we had 34 kilojoules. It was a positive, so 2 times 34. And then for our second reaction, we reversed it, so we had to put the negative sign, and we also doubled it, so we times by 2. So there we go, 68 plus 112. This is positive 180 kilojoules. This is an endothermic reaction. So we can just say, thus the enthalpy of formation for 2 moles of NO is 180 kilojoules. If we wanted to say per mole of NO, we would just divide that by 2, and we have 90 kilojoules per mole. I'll see you tomorrow.